So Unit 5 is a collection of different topics that you should have some acquaintance with. We're going to shift gears again and talk about a different kind of transistor. We're getting ready to talk about bipolar transistors. A bipolar transistor consists of two p-n junctions. So before I dive into bipolar transistors, I'd just like to review a few key concepts from p-n junctions, and then we'll be ready for bipolar transistors. So there's a large collection, a large number of transistors. We focused on MOSFETs. Now we said a little bit about HEMTs as well. There's also another class of transistors called bipolar transistors. There are different flavors. BJT is bipolar junction transistor. HBT is hetero junction bipolar transistor. DHBT is double heterojunction bipolar transistor. We're going to talk about all of those devices in the next lecture. The important point is that those devices are barrier-controlled devices also, so the same concepts that we use to understand MOSFETs can be used to understand bipolar transistors as well. Okay, now a little bit of history. The field effect transistor is a relatively simple device, and you can see how a long time ago people conceived of the idea of using the field effect to produce a transistor. It was patented and worked on in the 20s and 30s. It took a long time to reduce it to practice. In fact, the R&D effort at Bell Labs in the late 1940s was directed towards trying to finally realize these field effect transistors. And what they stumbled across was a transistor effect that was a different type of effect. It was a bipolar transistor. This is a replica of that first transistor. You can see what it looked like. It'd be hard to predict the importance of this technology from this early prototype of where the effect was dominated. But you can see it sitting on a piece of germanium, the first semiconductor that was used for transistors. You can see that that slab of germanium is holding everything up. That's why it was referred to as the base, and that name has stuck. We still refer to one of the terminals of bipolar transistors as the base. Now, quickly after that, several years after that, a more manufacturable version of that bipolar transistor was developed. It was called a double diffused, a bipolar junction transistor, BJT. The structure looked something like this, and we will discuss it in more detail in the next lecture, or structures that look like this. The heart of the structure is an N-type region, a P-type region, and then another N-type region. We call this an NPN bipolar transistor. You can see that there are all of the contacts are on the top surface. The current has to flow in a 2 or 3 dimensional path to get out to the contact. The heart of the device is this NPN structure. If we look at that, we can think of that as an ideal one-dimensional bipolar junction transistor, and we will be drawing pictures that look like this in order to understand how that device works. But always be aware that it's really a 2 and 3 dimensional device, and the current has to get out to the contacts on the top surface. Now, just as the MOS capacitor is the heart of a MOSFET, so we first developed an understanding of the MOS capacitor and then of the MOSFET. The p-n junction is the heart, the basic part of a bipolar transistor. So before we talk about bipolar transistors, we should make sure that we understand p-n junctions. So just a little bit to refresh your memory on p-n junctions. So here are two semiconductors, two identical semiconductor materials with the same band gaps. One doped N-type with a Fermi level up near the conduction band, one doped P-type with a Fermi level down near the valence band. You can see that if we put these together, we have to have one Fermi level in the one system at equilibrium. That means that we have to develop a positive voltage on the N side to pull everything down so that its Fermi level aligns with the P side. When we do that, we'll get an energy band diagram in equilibrium that will look like this. One constant Fermi level for both regions. Everything's been pulled down on the N side. We have induced a positive voltage on the N side called the built-in voltage, which lines everything up. Here's my N region, my Fermi level near the conduction band. Here's my P region, and there's a transition region in between. On the P side, which we'll look at in a little more detail, we have some concentration of holes on the p side. I'll label that as p sub p, holes on the p side. Since this is an equilibrium diagram, I'll label that as p sub p naught, the equilibrium hole density. And this is just a p-type material. Its hole concentration will be equal to the doping density at room temperature. There will also be some equilibrium concentration of minority carrier electrons on the p side. I'll label that as NP naught, the number of electrons on the p side in equilibrium. And you'll remember that NP is equal to Ni squared in equilibrium. So the number of minority carrier electrons is a very small number, Ni squared divided by the p-type doping density. So that's the situation in equilibrium. Under forward bias, the p-n junction will look like this. We will apply a positive voltage to the p side, or I could apply a negative voltage to the n side, it doesn't matter. The positive voltage on the p side will pull everything down and split the Fermi levels. We now call them quasi-Fermi levels. So we'll pull the quasi-Fermi level for holes down on the p side. It'll be below the quasi-Fermi level for electrons on the n side. The important point to note is that we've pulled everything down. The voltage will drop on the most resistive part of the structure, which is the transition region here, where there are the fewest number of carriers. And that means that this energy barrier has been lowered. It's been lowered from Q times the built-in voltage to Q times the built-in voltage minus the forward bias. So we have lowered the energy barrier between the n-type region and the p-type region. That means that it's going to be exponentially more likely that electrons can hop over that barrier and be thermionically emitted into the p side. That means that the concentration of minority carrier electrons on the p side is going to increase exponentially with the applied forward bias. Right? So this is forward biased injection. And we will assume that the ohmic contact has a property where it's a highly defective surface. Any minority carrier electron that reaches that surface immediately recombines. So we will always maintain the equilibrium concentration there. We can't get away from equilibrium because the excess electrons that have been injected recombine immediately when they hit that metal contact. Now, we have also lowered the barrier for hole injection into the n side. Remember, these are always electron energy band diagrams that we are drawing. Electron energy versus position. Hole energy increase is going down. So this is an energy barrier for holes. The energy barrier for holes has also been lowered by the forward bias. So we're going to inject holes onto the n side. We'll have increased exponentially the concentration of minority carrier holes on the n side. Now, if we ask what current flows, we've exponentially increased the probability that electrons will be injected from the n side to the p side. If I look at what happens in the n side, if the n region is short so that the electrons don't recombine in the n region, what they will do is we've exponentially increased their number at the beginning of the p region. We have maintained their number to be where it was in equilibrium, so no excess electrons at the contact on the end of the p region. If there's no recombination in between, we just get a straight line profile. And whenever you have a concentration gradient, we know that mobile particles will want to diffuse down the concentration gradient. So electrons will diffuse down that concentration gradient, and they'll diffuse across the p region and then go out to p contact. The flux of electrons is given by Fick's law of diffusion minus the diffusion coefficient of electrons times the concentration gradient. The current then is just the charge on an electron minus Q times the flux of electrons. So we can very simply then see what the electron current will be. We know the concentration of electrons at the beginning of that region. It has increased exponentially from its value in equilibrium, so the excess concentration is its new value minus its equilibrium value. The concentration at the contact is 0. The concentration gradient, we just divide the maximum by the minimum and then divide by the width. So we can plug everything into these expressions. We get a very simple expression for the electron current due to forward biased injection in this PN diode. Now just notice, I'm not worrying about signs, I'm not worrying about whether the electron current is flowing in the plus X or minus X direction. I'm only worrying about the magnitude of the current in this case. So we have a very simple relation for the injected electron current. At the same time, holes are being injected. I'll have an exponential increase in the minority hole concentration at the beginning of the N region. My metal contact on the N region will maintain the excess concentration as 0, maintains equilibrium conditions. Holes will diffuse down the concentration gradient. I'll have a flux of holes that's given by Fick's law again. I'll have a hole current. The charge on a hole is plus Q. I'll put that all together again, and I'll get a very similar expression for the hole current due to injection of holes in the N region. It'll depend on the equilibrium hole concentration, on the hole diffusion coefficient, on the thickness of the region across which it's diffusing, and then exponentially with forward bias. So we can very simply then get a description of the forward biased injected currents due to electrons and holes in the PN junctions, and these are the two expressions that we get. We will use these expressions extensively when we develop an understanding of bipolar transistors. The current then that flows through the contacts is the sum. That's why this device is called a bipolar device. It has both electrons and hole currents. If we want the total current flowing through the terminals, we add the two together. Now, we're also going to be talking about heterojunction bipolar transistors. A heterojunction bipolar transistor makes use of heterojunction diodes. What's a heterojunction diode? Well, a heterojunction diode would be made of two different semiconductors. So, for example, if I were to make the N region out of a wider band gap than the P region, I would have a heterojunction diode. So if we were to do that, let's think about what would happen. I have a wide band gap N region. I have a smaller band gap P region. I'm showing them lining up so that their conduction bands line up, but their band gaps are different, so their valence bands are not going to line up. Now, in general, how these bands line up is a material-specific property that depends on the specific material systems. This is the way we would like them to line up. This is the best way for them to line up in a diode like this, where we are interested in electron injection. So that's the case that we will consider. This is the case that we would like to achieve, and technologists will work hard to try to achieve conditions that look like that. Okay, so we have a valence band discontinuity in this example, but no discontinuity in the conduction band. We're basically assuming that the electron affinities of the two semiconductors are the same. We put it together then and draw an energy band diagram. We have a small band gap P region. We have a large band gap N region. You can see that the band gap here is much wider than it is on the P side, and there will be a barrier to electrons, but there will be a much larger barrier to holes. So we have now produced two different barriers, a small one for electrons and a much larger one for holes. That's what the heterojunction does for us, and we can use that to great benefit. So you'll note that in this case we have all of the discontinuity in the band gap was translated to a discontinuity in the valence band. That's why we have the higher barrier for holes injected across that region. So the key reason for doing this, we'll see when we talk about bipolar transistors, is that this will suppress one of the two currents. This will suppress the current that we don't want, the injection of holes into the N region. But we have the same barrier for electrons injected from the wide band gap N region into the small band gap P region. We haven't suppressed that. That's the current that we're going to want in an NPN transistor. So how do we describe these? Well, it's very simple. We had these expressions for the injected currents. It was Q. There is a diffusion coefficient because they're diffusing across the region. There is a width of the region across which they're diffusing, but because that determines the concentration gradient. And then it depended on the minority electron concentration, Ni squared over the doping density on the P side, enhanced exponentially by the forward bias. For the homojunction, Ni squared was the same on both sides of the junction. In this case, we have two different intrinsic carrier concentrations. Because you'll recall that the intrinsic carrier concentration squared is proportional to e to the minus band gap over kT, and we have two different band gaps. So if the band gap on the N side is bigger than the band gap on the P side, then the intrinsic carrier concentration squared on the N side is going to be exponentially smaller than the intrinsic carrier concentration on the P side. The intrinsic carrier concentration on the N side is what appears in our hole current, so it's going to be exponentially lowered by the wider band gap. That's the key thing to take away from what we get by using heterojunction diodes. Much suppressed hole current in this case. All right, well, with that basic understanding or review of PN junctions, we're going to be able to understand how heterojunction bipolar transistors operate. So just a key summary of what you should recall about PN junctions. They're bipolar devices in general. The current is due to both electrons and holes. A forward bias barriers lowers the barrier for electron and hole injection across the junction. So this is a barrier controlled device. We're getting current flow by lowering a barrier. The current increases exponentially as e to the minus q forward bias over kT. That means a 60 millivolt increase in the forward bias increases the current through the diode by a factor of 10. That sounds like the 60 millivolt per decade, which is the fundamental lower limit for the subthreshold swing in a MOSFET. And it's the same thing because subthreshold current is due to injection over a barrier. Diode current is due to injection over a barrier. And the fourth thing to take away from this brief review is that it is possible to suppress one of those two currents by using heterojunctions. Okay, we're ready now then to take a quick look at bipolar junction transistors. An NPN bipolar junction transistor, or PNP for that matter, consists of two PN junctions. The NPN bipolar transistor, there is a shared P region. In the PNP, there would be a shared N region. Since we understand PN junctions, we should be able to understand bipolar transistors. That's what we'll discuss in the next lecture.